Hey everyone, it's David from Streaming Relativity, home of Astro DNA Observatory. I'm here speaking today about calibration frames in astrophotography, specifically dark frames, flat frames, and bias frames, and why they're important, and how we use them to improve our astro images. To do this, we probably want to start with understanding what noise is in astrophotography. And as astrophotographers, we use some very sensitive digital cameras, and we're trying to capture faint light signals in an otherwise very dark night sky. And the camera itself typically has either a CMOS sensor or a CCD sensor, and the job of that sensor is to register photons that are gathered and focused by the telescope onto the sensor surface. And during that process of registering these photons and then subsequently reading these photons, there's electrical noise that's generated, and it mixes with the signal, which is, of course, our actual image data. The calibration frames that we're going to talk about today, they help us to eliminate some of this noise and ultimately improve our images of celestial targets. And it's actually quite easy to build a library of calibration frames, and it's essential if you want to produce high quality astrophotographs. So it's important to note that there are different types of calibration frames. There are really three types of calibration frames that you should have in your library. And those include dark frames, which broadly they're used to remove what we call dark current that develops in the camera during the course of an exposure. And then, of course, we have flat frames, which are those are used to correct uneven illumination of the camera sensor that is typically due to the specifics of your optical train, your telescope, and the lens system that you're using on the mirrors that you're using. And then finally, there are what we call bias frames, which are used to remove noise that's inherent. It's fixed noise of the camera sensor, and it occurs for every exposure. It's always kind of present in the camera sensor itself. So those are the three types of calibration frames that we need to create to achieve decent images. So let's talk about dark frames first. I mentioned dark current, and it is an electrical noise that's generated mostly from thermal fluctuations that occur in the camera sensor. And the noise, this thermal noise, it increases with obviously the temperature of the sensor, but also the exposure time. So the longer that the exposure is, the difference between a 1 second exposure versus a 300-second exposure, you're going to have a different thermal noise pattern, and this is why so many of the dedicated astronomy cameras that we see today have built-in coolers. Well, dark frames are used to capture that noise so it can ultimately be subtracted from the actual signal that you're recording in your light frames. Light frames being, of course, the pictures that you're trying to take of the celestial objects. And dark frames are, they're captured by how do you create your dark frames? Basically, you want to create a total darkness scenario. So cover your telescope, be away from any lighted areas. I do this in my dome at night, and with the lens cap on. Expose your image sensor with the specific settings specific settings. So the temperature of your sensor should be known and set to what your image session will be. The exposure length should be the same as you'll be using in your lights. The camera gain setting and the offset, all of those settings need to be quite specific for your dark frames, and those settings must match those that you're using for your light frames in your imaging session. And the number of dark frames that you want to capture should equal the number of light frames in your imaging session. So if you're going to be doing 2,300-second exposures, you should probably grab 2,300-second darks. And again, use the same sensor settings for your darks as you plan to use for your lights in that session. Well, let's take a look at that. So here I'm showing a dark frame that was captured with one of my cameras, an ISI 1600 monochrome pro camera. It's a 300-second exposure. The temperature of the sensor was set to -10 degrees Celsius, gain of 75 and offset of 12. And as you would expect, it's a dark frame. It looks like a black frame. You might be wondering, well, what good is this, and how's it going to improve my image? Well, I also attached a histogram for the frame below, and you'll notice that largely there's no signal across the spectrum of illumination. But when we get down into the darkest regions, we see a spike here, and that happens to be signal data. And if we stretch this image just a little bit, suddenly the frame starts to look somewhat pixelated, taking on a gray tone. And if we look at the histogram now, which is a stretched histogram, we now see we do have significant signal in these frames. And in fact, if we take a 300% magnification on this, suddenly we look like we have a star field. And that is dark current in the dark frame, and we want to remove this from our images when we stack. So those are dark frames. Now, flat frames, we're dealing with a different type of noise for a variety, or a different effect. For a variety of reasons, a camera sensor is generally not evenly illuminated. And this is largely a result of the optics train, but uneven illumination can be caused by vignetting in the optics train, and vignetting is when we see darker regions in the outsides of the frame. Often it's an effect, an old-fashioned effect in photographs, actually, but it's not a wanted effect in astrophotography. And we also have a sensor that, regardless of its quality, is going to have non-uniform response characteristics of the pixels within that surface area. So some pixels are going to react more accurately than others. And that could lead to uneven illumination. And finally, there's always physical interference from dust on the sensor surface. And don't panic. Everybody's got dust on their sensors, and unless you're really lucky or you're completely obsessive. And I don't know how you can be about cleaning these sensors, but they are disturbing when you first see them. So flat frames capture these artifacts and allow us, enable stacking software to apply corrections to the signals, the good signals, during frame stacking. And this is accomplished through a normalization algorithm, which uses the flat frame readings to equalize the light frame signal. And you can research a little bit more about that if you want, but in essence, we're trying to make up for uneven illumination in the optics train. And so flat frames are created to do this, what you really need to do is supply a uniform light source, like a light box, or I often use an iPad with a white light background to cover my smaller telescopes. Anyway, you lie this light source across completely cover the aperture of the telescope, and you capture frames using specific sensor settings, including sensor temperature, gain, and offset. Note that I did not say exposure. I didn't mention exposure length here, and that's because unlike dark frames, flat frame exposure times are not dictated by your light frame exposure times. Rather, you should expose your image sensor with lengths that help you achieve what we would call a centered and evenly distributed histogram of light intensity. And you'll have to play with this for your for your equipment and your setup. But this could be anywhere as low as 300 milliseconds, and it could be high as several seconds or more, depending on your setup and how you've got your sensor. Sometimes there's software that can help you automatically choose that exposure time for you. But at any rate, just keep in mind that sensor settings should be the same as your light frames. However, exposure times should be just enough to get a nice even distribution in your histogram. And it's important to note, again, unlike dark frames, light frames are specific to your optical train, which means that the flat frames you're going to capture for one telescope will not be the same as the flat frame that you'll capture for a different telescope, even if you're using the same image sensor or camera behind it. And same thing applies to filters. Your one filter might have a different, you might need to do different exposure times with one filter for your flats versus another, and you should capture for, I capture for every filter. So I have my flats captured for every filter. Okay. How do we, let's illustrate flat frames. These are a little bit more obvious. So this is an unstretched capture. In this case, I'm using the same exact camera setup here, but you'll note that I've mentioned that I'm using my William Optics Zenith Star 61 with a luminous filter. And there we have our relatively centered, even distribution of light. But I wanted to, I stretched this anyway so I can bring out some of the issues of illumination a little bit more clearly. Here's your vignetting. You can see it all over the side, and by the way, this is just the stretched histogram. So this really emphasizes vignetting for you. But then if we do a magnify this corner of the frame, we see these dark circles, and they seem to be appearing at different levels and different intensities throughout the frame. Yeah, well, those are dust motes, and that is related to dust on the sensor, and obviously we have the vignetting a little more clearly illustrated here. So these are flat frames, and we want to capture these artifacts because we want to remove them from our final stacked image. The last frames we'll talk about are bias frames. Every camera sensor has inherent digital noise that exists in every frame regardless of the exposure time. Unlike dark current might grow and it's actually variable with exposure time, this is inherent fixed noise that relates to the electrical current that flows when we read out, not only then, but mostly when we read out on the sensor pixel array to see what values have been collected. And so bias frames are used to capture this noise so it can be subtracted, like similar to dark frames, from the actual signal recorded in your light frames. And bias frames are captured. This is kind of similar to the way we do darks. We cover the telescope lens completely, and we expose the sensor using the same settings that we would when we're doing our light frames, but the difference is that the length of the exposure is going to be the shortest possible length that we can set for the camera. The reason is we're just looking for that readout noise. And so like dark frames, bias frame camera settings must match those used for your light frames. Just take it at the shortest exposure time possible for your setup. And I like to shoot my bias frames and I'm shooting my darks just for convenience because the telescope is covered and because they have to share the same settings. This is a really easy thing to do and there's no harm in doing them together and collecting this information in your library all at once. Okay, so looking at bias frames, you would expect, why isn't it totally dark like our dark frames? Well, that's because there's an offset and gain that I used here, which I did not label, and I apologize for that. I'll probably make an edit to this video. At any rate, I think I shot this with a gain of 139 and an offset of 21. Which is prescribed for the ASI 1600s, one of the presets that they recommend. You'll see that this is a brighter image because of that gain and because of that offset. There is illumination even in a dark frame, and in this case it's centered. Stretching it brings it a little bit more, shows the noise a little bit better, and then finally magnifying at 300%, you'll see that there's quite a bit of this very noisy noisy pixels that ideally we would like to remove from our images. There's the data we were looking for, guys. Perfect. So that's your bias frames, and and look, does this work? Does it actually produce make a difference? It really does. This is an image I shot 2 nights ago with the William Optics Zenith Star 61 luminance filter. This is really just 6 exposures at 300 seconds. Um, and the settings were -10 degrees, 75 gain, 12 offset. These 6 light frames with the calibration frames that I just went over resulted in a calibrated stack of M33. This is Triangulum Galaxy. Very simple linear stretch. I did nothing to process this. This is the result after stacking with calibration frames with a auto linear stretch, and it's not a bad grab actually. It was satisfying given that it was a very short session, 30 minutes worth of data, and produced something that I think is, it's actually remarkable. I love it. So at any rate, I hope you enjoyed the video and learned something from it. If you did, like it, subscribe. I have others coming. In fact, the next thing I'd like to do is just go over back focus and field flatteners. I recently went through an exercise of adjusting my my William Optics 61 with its field flattener. So I'm going to go through that in detail because sometimes people get confused about that. Again, I'm David, Streaming Relativity, home of Astro DNA Observatory. All the best.